Our next speaker is going to be Maria Tsantaki, who's going to tell us about lithium giants and open cluster.
Hello, everyone. Thank you for being here. Today, I will talk about my work on the search of lithium giants in open clusters with high-resolution spectroscopy. This work is conducted with my collaborators at the Institute of Astrophysics and Space Science in Porto, and also at my institute at the Osservatorio Astrofisico in Arcetri in Italy. So we saw this figure before. I will explain it briefly. Lithium is a very interesting element because it can be an excellent tracer of stellar evolution. So in the last years, there are a large spectroscopic surveys dedicating on measuring lithium very successfully. And in particular, the GALA survey has delivered the lithium abundances for 100,000 stars, low mass in the field. Kumar et al. Presented this work of lithium abundances as a function of luminosity. And they show the post-evolution of post-main sequence evolution of lithium. So in this plot, I don't have a pointer, but you can follow me on that. We see that as a star leaves the main sequence, the convective envelope deepens, and therefore the lithium becomes diluted. So the lithium decrease continues until the luminosity bump, and there lithium gets destroyed until it reaches the RGB tip. The model predicts that after that, lithium in the red clump should be lower or equal in abundance, at least as the lithium in the RGB tip. However, the data show that the lithium abundance for these stars is much higher. The next year, Magrin et al. Studied a similar picture by using the GAISO data, or low mass stars again, but in open clusters. And clusters are ideal environments to study lithium because we can constrain the evolutionary stage of the stars better. The authors warn us, though, that the measurements of the lithium for the stars could be upper limits, and the inclusion of new models with additional mixing could make the lithium enrichment for these stars not so ambiguous. So this work is focusing on open clusters that I mentioned before have the advantage of constraining the evolutionary stage better. So we can identify which mechanism of enrichment is responsible in these cases. The sample in this work is based on Planet Search program around the world of stars. This is a 17-year project, which is still ongoing, using HARPS data. We have 250 stars in 32 different open clusters where the parameters and lithium abundances were derived using the spectral synthesis technique. We also validated temperature and gravity using external methods, namely photometry and astrometry for the surface gravity. We derived ages and masses using isochronous feeds and based on the methodology of Bossini et al. I want to point out that the masses in the sample are quite wide. They go from up to 6 solar. Finally, we have 17 stars with lithium abundance above the classical limit. Now the question is, if are all these stars real lithium-rich giants, or are the only ones that exist in these clusters? Below I show the two plots of the distribution of the signal-to-noise of our spectra. We took only the spectra of stars higher than signal-to-noise 30. And also on the left side, I show the distribution of the iron abundances for these clusters. So the first cluster I present here is NGC 6705. And in this cluster, we find 13 classical lithium-rich stars. I want to point out also that most of the giants in this cluster have lithium abundance above 1 dex, which means that the main sequence progenitors may have lithium content very high, So after the depletion, the destruction, the giant stars reach to the current state. So the lithium-rich giants in this cluster lay on the base of the RGB phase, but also they are ascending. So which mechanisms are responsible for this enrichment? There are several mechanisms proposed in the literature. For example, at the luminosity bump, we have the Cameron-Fowler mechanism, but this works only for low mass stars, which is not our case. At the Ren Club, there are two mechanisms proposed based on the mixing at the helium flash due to internal gravity waves, also induced by neutrino magnetic moment, again for low mass stars, which is not the case. And we have also the enrichment due to the Cameron-Fowler mechanism triggered by the hot bottom process. I guess, again, not in our case because this is for the HGB stars. The two external mechanisms that were discussed also in the previous talk have to do with planet or brown dwarf engulfment and tidal interactions in binaries. These processes can have a signature on the star by leaving a higher SNI. In fact, the stars are not binaries, but in fact, they show some some correlation of lithium abundance with SNI. Clusters have also the advantage to help us constrain the limit of what we consider a lithium-rich giant. The literature limit at 1.5 is set by models, but in clusters, we can know the maximum lithium abundance of the progenitors. So here are the results based on the GAISO data from Romano et al. And Maglin et al., where the authors measured the average maximum lithium abundance as a function of the cluster metallicity. So this means that this is the abundance of the lithium before depletion. So for example, for the cluster I mentioned before, only 5 stars are above the limit if we consider the results from the GAISO survey instead of 13 that I mentioned before. And for the whole sample, the percentage of lithium-rich giants using the classical limit is 6.5, but we use the maximum lithium abundance of the progenitors is around the same though, but for different stars. So if we use the latter criteria, we have identified 4 clusters that host lithium-rich giants, and they are in a variety of evolutionary stages. At the bottom, I show the spectrum of the stars of the whole sample. They are classified from lithium poor to lithium rich, and at the top, it's the HR diagram. So the stars are located at the RGB from left to right. RGB phase, clump, RGB tip, clump, RGB tip. The lithium giants are at the yellow points. Another criteria I want to mention how to classify lithium-rich giants is by looking at stars at the same evolutionary stage and comparing the strength of the lithium lines. This is what is defined in the literature as lithium-rich giants in context. So in this case, we have five clusters where we have identified these objects. They are in the HR diagram pointed as stars. So from left to right, we have 2 stars that they are located at the luminosity bump. Then at the luminosity bump, in the middle at the luminosity bump. Then 2 stars, they are located at the bottom of the RGB phase, one at the tip, and the final cluster, we have 2 that they are at the tip. I want to say a few words for the work of Ines Rollo, who finished her master. Now she's in the pursuit of a PhD where she analyzed the same data set, but this time she looked at the time series of our data. And she calculated activity indicators and tried to find correlations with lithium. So she found out that the standard deviation, the peak-to-peak amplitude of the bisector and the full width have maximum of the SSAF, and also the mean and median H alpha increase exponentially with lithium abundance. I want to point out to her paper and her poster for details. So I will conclude and by telling that the number of lithium-rich giants depends on the classification criteria, and they are found in various evolutionary stages where multiple mechanisms may be responsible for their enhancement and not just one unique one. And the percentage may differ from the field one. And also there are hints for correlation between activity and lithium. Thank you. What is the name of the cluster? No, we didn't have probably the spectroscopic data for this.